Hello viewers. In the last lecture we have discussed the architecture and organization of microcontrollers in general, and we have seen that there exist a large number of microcontrollers, and in this lecture we shall consider the architecture and organization of the most popular microcontroller, the 8051. So let us first consider the major features of the Intel 8051 microcontroller. First of all, it is a 8-bit CPU. The CPU of this microcontroller 8051 is 8-bit. That means most of the registers, the ALU, all will be of 8-bit, and ALU operations, arithmetic and logical operations also will be of 8-bit. So it has got 8-bit CPU. It has got on-chip oscillator. As you have seen, that this is one of the major function of microcontrollers. The microcontrollers are provided with on-chip oscillator. Let's see how this on-chip oscillator is provided in 8051. So in 8051 we have got the on-chip oscillator in this manner. There are two pins, XTAL1 crystal 1 and XTAL2 pin number 18 and pin number 19. These two pins are provided. Obviously the oscillator is inside. This is the oscillator which is provided inside the chip. This is the chip, and this is where the clock comes out. But externally we have to connect one crystal. A crystal has to be connected externally between these two pins, and the clock frequency of this crystal can vary from 1.24 megahertz to 12 megahertz. This is the range of frequency over which this particular microcontroller will work. However, it will require two additional components, two capacitors of low value, say 30 picofarad, so that the crystal oscillates, the oscillator oscillates at the fundamental frequency of the crystal. Otherwise, if these capacitors are not there, the oscillator can oscillate at some harmonic frequency. To suppress oscillation at harmonic frequency, these capacitors are necessary. And the clock is generated in this way inside the chip, and this goes to the inner part of the circuitry. And the clock is available. I am drawing the clock, and how it is used I shall explain. So it has got two phases, phase 1 and phase 2, P1 and P2. These are the two phases of the clock. Inside the chip, it operates on two phases. We have already seen that two-phase clock is useful for operation of the circuitry, and two-phase clock is used here. So this is phase 1, this is phase 2, and so on. So alternately P1, P2, P1, P2. So this is how the clock is generated. Then each of these, this phase 1 and phase 2, this particular clock, consisting of P1 and P2, form the state S1. This is state S2. This is state S3. This is state S4. This is state S5. This is state S6. So these 6 states forms one machine cycle. You will see that most of the instructions will be expressed, can be executed using a single machine cycle. However, there exist several instructions where you will require multiple machine cycles. But most of the instructions will be executed in one machine cycle comprising 12 clock pulses, and each clock pulse having two phases P1 and P2. And there are two ALE signals. ALE signals are generated for latching the address for fetching instructions. There are two ALEs which are generated within a single machine cycle. So this is one ALE and this is another ALE. So this is starting from the S2P1 to S1P2 to S2P1. Similarly, this one is S4P2 to S5P1. So these two, the purpose of these ALEs is, two ALEs is, this particular address latch enable is used to fetch the instruction from the memory, and if in that instruction, if there is another additional memory reference is required, you have to fetch another byte of data, then this ALE is used. However, if that instruction does not require fetching of two memory locations, then this ALE is ignored. That means if an instructions involve fetching 2 bytes of data, one instruction and another operand, then it can be executed, or both the bytes can be fetched in a single machine cycle. So that's why two ALEs are generated. So this is how the oscillator works, and the clock is generated, and how the clock is interpreted in terms of number of states and machine cycles. So this is the function of the on-chip oscillator. Now it has got other functionalities like 4K bytes of on-chip ROM and 120 bytes of on-chip RAM. So as you have seen, the important characteristic of microcontrollers is that the RAM and ROM will be on chip, of course of limited size. In case of 8051, we see that 4 kilobytes of on-chip ROM is provided and 128 bytes of on-chip RAM is provided. And let's see the memory organization or the memory map of the microcontroller. Here, first of all, we shall consider that the on-chip part of the RAM. So let's assume this is the internal this is your internal RAM. This is your internal ROM. Internal ROM 4 kilobytes, and it starts from 0000 to 0FFFF. This is your internal ROM, and in this case, how do you know that the data is coming from internal ROM or external ROM? Because for the sake of flexibility, there is a facility for having external ROM as well. So there is a pin known as external EA or external address. If that is 1, then it is internal ROM. On the other hand, if the EA pin, that external enable, external address pin is 0, then it is external. In such a case, the ROM comes from the external ROM. So this ROM forms the program memory. And however, whenever you are using this pin EA, external address, and for connecting to ground, that means your memory is external. In such a case, you can have a very large memory up to 64 kilobytes. So your external ROM can be from 0000 to FFFF, and here this is one part from 0000 to 0FFF, and also from 0FFF. Sorry, it will be from 1000 to FFFF. This is your external RAM, external ROM, and which is used for program memory. So If EA pin is connected to 1, then you don't have the external ROM or external memory, program memory. However, whenever this 2K, if 4K is not sufficient, on chip you have got 4K RAM starting from 0000 to 0FFF. If this is not adequate, only then you go for external ROM. Otherwise, this internal ROM is sufficient. Similarly, so far as the RAM is concerned, we have seen there is 128 bytes of on-chip RAM. Let's see how this on-chip RAM is provided. This on-chip RAM has got two parts, we can say, starting from 00 to 7F. This is your internal data RAM. Internal data RAM. And from 7F to FF, this part is also available inside the chip, but here the special function registers are mapped. We shall see how these special function registers are mapping on the internal RAM address. However, whenever you are using external RAM, that is also allowed. Whenever you have got that EA pin connected to 0, in such a case you have got external RAM, and whenever you have got external RAM, external data RAM, which is from 0000 to FFFF. So you see, simultaneously you can have external RAM starting from 0000 to FFFF, and also you can have internal RAM from 00 to FF. However, only 120 byte is used as data RAM, and for another 120 byte, out of that 120 byte, some of the locations are mapped by using those special function registers are mapped onto this part. So this is how the on-chip RAM and ROM is provided in your 8051. Now, it has got a number of registers, particularly it has got 21 special function registers. And before I discuss the special function registers, let us consider the register organization in general. As you know, a particular processor has got some general purpose registers and some special purpose registers. So you have got general purpose registers, and special function registers. Let us see in what form these general purpose registers are available. You will find that in your 8051 you have got 8 banks of, sorry, 4 banks of 8 registers. That means in each bank you have got 8 registers, which is also mapped on the RAM, internal RAM. So these registers which are used as general purpose registers as scratchpad memory, you can store some intermediate data while executing program. It is available in 4 banks, each of 8 registers. And let's see how it is done before we discuss the special function registers. So we have seen that the internal RAM which is available inside the chip is from 00 to 7F, and then 7F to FF is special function registers. Now the internal RAM can be divided into 3 distinct parts. The first part, you can consider it as working registers. These are the working registers. As I said, these are available in 4 banks, bank 0, bank 1, bank 2 and bank 3. And they are either accessible as register R0, R1, R2 up to R7 of bank 0, or register R0 to R7 of bank 1, or register R0 to R7 of bank 2 or registers R0 to R7 of bank 3, they are also accessible as memory locations, RAM locations. In such a case, their addresses are 00, 01 and up to 1F, 001F. And at a particular instant, we will see that only one bank is available. Out of these 4 banks, at a time, one of the 4 banks is accessible to the programmer, and that will be selected with the help of some flag bits of the program status word that we shall see. Then then another 202 2F, that means 16 bytes. These 16 bytes are available as bit addressable. What do you mean by that? You can access each of these bits independently. That means you can access bit 0 of memory location, RAM location 20, bit 1 of RAM location 21, and their corresponding bit addresses are 00 to 07 whenever it is part of 20 memory location. Then it is say 10 to 17 and so on. In this way it goes from up to 78 to 7F. That means 00 to 7F are the bit addressable RAM locations, which is in the range of 20 to 2F. That means whenever you are accessing as a byte, the location is 20 to 2F. On the other hand, whenever you are accessing as bit, then it varies from 00 to 7F. So you have got special instructions for accessing these bits, and you can manipulate them. Later on we shall see what are the bit manipulation instructions available. Then the third part, which is available as general purpose applications. This is available as general purpose. That means here you have got 32 bytes, 8 into 4, 16 bytes. Remaining memory locations from 30 to 7F. These RAMs are that is your data RAM, are available for general purpose uses. You can store your data, intermediate data here. You can also part of it can be initialized for stack. That means you can use this RAM as stack, or you can use them for storing data. So this is your internal RAM organization, which also shows how the registers are organized. Then comes the special function registers. We have seen that, we have already mentioned that the 8051 has got 21 special function registers, and the special function registers are shown here. A stands for the accumulator. Accumulator usually performs the same role. That means whenever you perform arithmetic and logical operations, one of the operands always comes from the accumulator, and result is also stored on the accumulator. So this is the accumulator. B stands for the is also a register, but this is commonly used for multiply and divide. That means whenever you are multiplying, the part of the result is stored in this register B, and whenever you are dividing, you are executing divide instruction, then also this register is used. Otherwise, this can be used as a general purpose sketchpad memory register. Then you have got DPH, data pointer. Data pointer has got 16 bit. However, it is available as 2 bytes, data pointer high and data pointer low. This is used for accessing external memory addresses. Then you have got interrupt enable IE. We shall see how by using this interrupt enable register you can enable or disable interrupts. Then IP stands for interrupt priority, with the help of which priority of these various interrupts can be assigned. Interrupt priority, later on we shall see, you have got 2 levels of interrupts. The priority can be assigned with the help of this register IP. Then we have seen that, as we shall see, there are apart from these 21 registers, there are 32 IO ports. which are available as 4 8-bit ports, 4 8-bit ports, P0 to P3. So for each of these registers, each of these ports, you have got a corresponding data buffer. So this is your P0 stands for IO port data buffer, P1 IO port, that means that this is the data buffer for port 1, P2 is the data buffer for port 2, P3 is the data buffer of port 3. So these are the port data buffers, and where these are mapped, the addresses where these registers are mapped, as we have seen, the higher order byte of address, that means 7F to FF, that means this 128 byte, where these special function registers are mapped are shown here. Accumulator maps on 0E, A0 memory location, B maps on F0, and so on. And then you have got some other registers. PCON stands for power control, which maps on memory location, RAM location 87. PSW stands for program status word, which maps on D0. Then you have got SCON, which is used for serial control, which maps on 98. You have got SBuffer, which is actually serial data buffer, which maps on memory location, RAM location 99. Stack pointer, here you note the stack pointer is only of 8-bit. That means your stack has to be in the internal data memory. The stack cannot be mapped to external data memory because your address is restricted to 8-bit and it has to be part of the internal data RAM. Then you have got TMOD, with the help of which the timer mode control can be set, and it maps on 89 RAM location. Then TCON, timer counter control, which maps on 88 RAM location. And for each of these timers, there are two timers, timer 0 and timer 1. For each of them, there are 16-bit registers. This is the lower order byte, TL0, timer 0 lower order byte, which maps on 8A RAM location, timer 0 higher order byte maps on 8C RAM location. This is your timer low high, timer lower order byte on maps on 8B, and this is your timer TH1 timer higher order byte, which maps on 8D memory locations. So we see we have seen that these are the various registers, special function registers, which can be accessed either by their symbolic names A, B, DPH, DPL, and so on. There are instructions where these symbolic names can be used. Otherwise, they can be also accessed in terms of the RAM locations, which are given here. Moreover, you must have noticed that there are some registers where I have given star. These are bit addressable. That means you can perform bit manipulation operations on these special function registers apart from those 16 bytes which are available. That means this part of the RAM is bit addressable, and also some of the special function registers like A, B, interrupt enable, interrupt priority, all the port lines, serial control port, timer control port lines, these are all bit addressable. And we shall see the need for this bit addressability. So these are the special function registers. So apart from this IO port lines, you have got two timer counters. As I have mentioned, two timer counters, each of 16-bit, and we have seen these are the counters, corresponding counters, which can be accessed by their symbolic names or by their addresses. Two timer counters, and then you have got a full duplex serial port. There is a serial port which is available in full duplex form, and the serial port can be controlled with the help of this timer mode control register and timer control resistors. So these two resistors will play an important role in controlling the resistors, with the help of which you can, this is for timer control. This serial control is SCON and SBUF. So serial control can be performed with the help of the serial port line, and this will act as a buffer, SBUF, for that serial port. That means full duplex serial port has got a control register and a buffer registers available. Then apart from which is available on chip, there is facility for having external RAM and ROM, as you have seen, and that facility can be extended to have 64 kilobyte of external program memory and 64 kilobyte of external data memory. And we have seen this can be available with the help of that external address pin. If this pin is connected to ground, that means if this bit is low, then you can have external program memory and data memory, and we have already seen the memory map, corresponding memory map. You can have external program memory and external data memory. And then another important function I should discuss in detail, that is the Boolean processing capability. We have seen that there are 16 RAM locations, a number of special function registers are bit addressable. What do you really do with the help of this bit addressability? What you do with the help of this bit addressability, you can access each of these bits, and you may assume that there is a separate processor. There is a separate processor which is a Boolean processor, with the help of which you can perform bit manipulation operations on those RAM locations and special function registers. What kind of operations you can perform? You can perform, say, set a particular register bit, a particular bit can be set, you can clear it, you can complement it, complement a particular bit. Not only that, you can perform jump if set. If a particular bit is set, then based on that you can do the you can jump to a location. That means conditional jump instructions are available, and you can for any of these bit addressable location, you can do the jump based on if it is set, or jump if not set. And you can also do jump if set then clear. This type of instruction is also available, and also you can perform logical operations on any of these bits where the carry flag bit acts as accumulator for this Boolean processor. That means one of the operand comes from the carry flag bit, and another operand comes from these locations which is addressed, either the memory location or the special function registers, and the result of that bit manipulation is stored in that carry flag bit. So with the help of this special Boolean processor and special instructions available for performing Boolean operations, you can write very efficient codes, particularly for control applications. As you know, the microcontrollers are used mainly for control applications, where you have to set a you have to sense a particular line, you have to set a particular line, clear a particular line. Say you have to turn a particular light, LED, turn off a light, turn on a relay, turn off a relay. This kind of operations you have to do in your various process control applications, and in such cases these Boolean processing is very important, and it allows you to write optimum code for control applications. Then I should also mention that your 808551 has got a powerful interrupt structure. We have seen that interrupt structure plays a very important role for real-time control applications, and a powerful interrupt structure is very important, and that's why this powerful interrupt structure is provided in almost all microcontrollers. Let's see how it is provided in your 8051. So 8051 provides you 5 external interrupts. So I should not write external, we shall see that some of them are really internal also. 5 interrupts apart from reset. Sometimes the reset is also considered as an interrupt. So if you consider reset as an interrupt, then the 8051 has got 6 interrupts. However, in some cases reset is not considered as an interrupt, but in some books or manuals you will find that the total number of interrupts provided in 8051 is mentioned as 6. In such a case, reset is included as one of the interrupts. However, you may exclude it in this particular case. We are considering that there exist 5 interrupts. So let us see what are the different interrupts available in 8051. Interrupts, their functions, then the vector address and the priority, if any. First of all, you have got one external interrupt, INT0. This INT0 is an external interrupt and which is available on pin 3.0, port pin P3.2. So port 3.2, that means on port 3, pin number 2 is the source of this interrupt 0. You will see that later on we shall discuss in more detail. The port lines are multifunctional. They perform dual functions. So here that port pin 2 of port 3 acts as an external interrupt input, and the corresponding vector address is 0003H, and it has got the highest priority. Then you have got timer 0. We have seen there are 2 timers. For timer 0, there is an interrupt, and this interrupt occurs when there is an overflow of timer 0. So you see, it is not an external interrupt, but interrupt is generated internally whenever there is an overflow of this timer 0. So it counts up, and whenever there is an overflow, then this interrupt occurs and it activates. There is an internal flag bit. That internal flag bit is TF0, timer flag 0. The corresponding vector address is 000B in hex, and it has the next highest priority. Then you have got another external interrupt, interrupt 1, and this external interrupt is available on pin port 3.3. That means on port 3, pin number 3 is the source of this second external interrupt, and the corresponding vector address is 0013 in hex, and it has the next highest priority. Then you have got another timer, timer 1, and timer 1 has a corresponding interrupt which occurs when there is an overflow of timer 1, and it activates TF1 flag bit, and the corresponding address is 001B in hex. Finally, as you have seen, there is a full duplex serial port, and there is a corresponding interrupt for this, and this interrupt occurs whenever there is completion of transmission or reception, and whenever there is a, as you know, in case of serial mode of data transfer, you write a byte into the buffer, then that particular byte is transferred serially, and whenever that transmission is finished, then there is a flag bit, that is your TI, that flag bit will be set and interrupt will be generated. So TI for transmission, and similarly whenever a particular byte is received, the processor will be interrupted and a corresponding flag bit receive interrupt will be activated, and the corresponding vector address is 0023 in hex, and this has got the lowest priority. So the priority is in this order. The internal that interrupt 0, that is this external interrupt, has the highest priority, and this serial interrupt has the lowest priority, and the priority is in this order. That means timer 0 has the next highest, interrupt 1 has the next highest, and so on. So this is how the interrupt varies. Now let us see, apart from this interrupt, as I said, each interrupt can be individually disabled or enabled. How they can be disabled or enabled? There is a resistor. We have seen that resistor is known as IE, interrupt enable resistor. That interrupt enable resistor has got bit lines: interrupt enable, next bit is not used, next bit is not used, then ES, ET1, EX1, ET0, EX0. That means whenever you set, that means whenever this bit is 1, that interrupt is enabled. If this is 0, the entire interrupt system is disabled. You can disable all the interrupts by making this bit 0. Similarly, this ES stands for that serial interrupt, ET1 is that timer 1 interrupt. You can enable by setting it 1, you can disable by setting it 0. Similarly, EX1 is that external 1, and that means IT this one, that IT1 and IT0. This is your external 0, this is your external timer 0, I mean enable timer 0. So these are the various bits of that resistor, and you can set or reset them to enable or disable various interrupt. Not only each of them individually you can say enable or disable, the interrupt system, all the interrupts can be enabled or disabled with the help of this bit. Then apart from this, each of these interrupts can be provided with 2 priorities. It provides you, that means each source can be programmed to 2 priority levels. It provides you only 2 priority levels, 1 and 0, and that can be done with the help of that IP register, interrupt priority register. There also the higher order 3 bits are not used, and then PS stands for the priority of the serial line, then PT1 timer 1, then priority of external interrupt 1, and then your priority of timer 0, and this is your priority of external timer 1. That means if these bits are 1, that means suppose you make this bit 1, then the external interrupt 0 has the higher priority level. If it is 0, then it has got the lower priority level. That means among these 5 interrupts, you can individually program each of them to either to higher priority or lower priority level. So in such a case, how the interrupt system will occur and how the interrupt will be accepted. Obviously, whenever a higher priority interrupt service subroutine is in progress, lower priority interrupts will be disabled automatically. And only when interrupt of the lower level is of the higher level is execution. Suppose this particular bit is set to 1 and this particular bit is set to 0. That means external interrupt 0 has the higher priority and external interrupt 1 has the lower priority. And whenever the interrupt service subroutine of this external interrupt 1 is in execution, and if this interrupt occurs, then it will be accepted and it will jump to interrupt service subroutine for external interrupt 0. On the other hand, if suppose interrupt service subroutine for 0 is in execution, and if this interrupt occurs, external interrupt 1 occurs, then it will be ignored because it has got lower priority. That means you can program them to higher or lower priority as per your requirement, and only when a lower priority interrupt service subroutine is under execution, a higher priority interrupt will be accepted. Otherwise it will be ignored. Okay. So you see, this much of flexibility is provided in the interrupt system, and whenever, as you know, in case of interrupts, first of all, it has to be a last instruction of a machine cycle. That is the condition. Then it should not be executing modification of this enable interrupt, or this your I is modifying this I register or IP register, or it is not executing one that RET1 return from interrupt instruction. So whenever you are not executing these 3 instructions and it is not last machine cycle of an instructions and no higher priority interrupt is under execution, the interrupt will be accepted. Otherwise they will be ignored. So this is how the interrupt system works in case of your 8051. Now, as I mentioned, the reset is also considered to be another source of interrupt. And how the reset can be activated? You can activate it by holding the reset pin to high level for 2 machine cycles. 2 machine cycles means 24 clock cycles. And whenever you want to make it power on reset, how will you do that? It can be done by using some external resistors, external capacitor, as you know. So this is your VCC connected to the processor. This is your 8051, and you can connect one capacitor, say 10 microfarad typically, to that RST VPD pin. So to this RST VPD pin is connected, and whenever you turn the power on, this capacitor is discharged. There is no charge across it. That means as you turn the power on, VCC, this capacitor will act as a sorted line. That means the VCC will be available here, and only after some charge is accumulated, the voltage will be below the threshold voltage. That's why this line goes to a Smith trigger. Here you have got a Smith trigger, so that small change of voltage on this line does not lead to spurious reset, and the output of this goes to that internal reset circuitry. Not only that, this reset pin can also be used for standby power. That means whenever power fails, it can be used to provide power to the internal RAM. How it can be done? Internally, the circuitry is like this. There are 2 diodes. One is coming from that external VCC. This is your VCC, and here you have got your internal RAM. This is your internal RAM, and this is your ground, that is your VSS substrate. So this is your VCC and VSUB. Normally power is coming to the internal RAM through this source. So but whenever power goes down, you see power may come from this line. So what can be done? The power either can come from VCC when there is no power failure, and when there is power failure you can connect one standby power to this line, maybe from battery or some other source. Then the power can come from the reset line to the internal RAM. So that's how you can give some battery backup to the internal RAM with the help of this reset pin. So this is the internal circuitry of the reset part of the circuit. You can see not only does the resetting on power on, but you can connect an external supply voltage, maybe from battery, which will store internal RAM information as the power goes off. And as you can see, it is done with the help of these two diodes. Now, whenever the reset is activated after this line is held high for 2 machine cycles, then you can see the resistors will be initialized with these values: program counter with 0000, accumulator with 00, B with 00, program status with 00, stack pointer with 00. You can see here program status word functions. It has got several flag bits like carry, accumulator, then overflow and parity. And this particular RS0 and RS1, as I was telling, you can select the register bank, one of the register bank at a time. That will depend on the value of these 2 bits of the program status word. Initially, you are making them 00 whenever you are resetting it. As you can see here, you are making them 00. That means as you turn the power on, register bank 0 will be available, and subsequently by modifying these 2 bits, you can access other register banks, RB0, RB1, RB2 or RB3. And similarly, the port lines are made FF, that interrupt priority is made, all are made 0, that means program to lower level. Interrupt enable, all are disabled, as you can see, 0, XX, 0000, then T mode is 00, T con is 00, all are initialized with 00. So you see most of the registers are initialized with 00 except stack pointer, which is initialized with 07. That is the address of the stack pointer as you turn the power on, and the interrupt system is disabled and priority level is made 0. So this is how the reset operation is performed. Then apart from this, the as you have seen, the 8051 provides you 4 kilobytes of ROM, 128 bytes of RAM. That may be inadequate. And also you have got 4 8-bit parallel ports. Now, to provide you more flexibility for larger external RAM, external ports, the ports are made multifunctional. How? Let us see. Out of these 4 ports, say port 0, this port 0, whenever you are not accessing external memory, it is acting as a normal port. However, whenever that external address pin is grounded, then this port 0 provides you the lower order byte of address. That means A0 to A0 to 7 is available on this port line, because the microcontroller is not having external address lines A0 to A15. So if you want to access some external memory, it has to be provided through some port lines, and the port 0 provides that. Then you have got port 2, which provides you the higher order byte of address, that means A8 to 15. So this is your higher order byte of address. Then port 3 is also multifunctional. For example, P30, 31, 32, 33, 34, 35, 36, 37, all are multifunctional, which is used as RxD, that means receive line for the serial data transfer, TXD, transmit line for the serial data transfer, and we have already seen this is acting as external interrupt 0, this is acting as external interrupt 1, 3.4 is the timer input, input for the timer 0, this is acting as input for the timer 1, and these two will act as write and read control. So these port 3 lines are also multifunctional. So port 0, port 1 and port 3, these three ports are multifunctional, and with the help of which you can interface external memory of any size up to 64 kilobytes, both RAM and ROM, and also you can interface general purpose ports like 8255 if 2 ports or 3 ports are not sufficient. Similarly, with the help of these port 3 external lines, you can perform serial data transfer, provides you external interrupts, timer inputs, and read write for accessing external memory. Now, before I conclude our discussion today, I would like to discuss the Intel 8051 family. The 8051 is so popular that not only Intel but many other companies have come up with their version of 8051, and so 8051 is available from different sources with variety of capabilities, and this is summarized in this particular diagram. The original one, the Intel 8051, has got 4 kilobytes of ROM, as you have seen, program memory, 128 byte of RAM, 32 bits IO lines, one serial port, 2 timers, and 6 interrupt lines, including the set. 8031 is ROM-less. ROM-less means ROM is external to the chip, and so internally there are 0 kilobyte of ROM. RAM is same, 128. It is exactly same as 8051, except that ROM is external to the chip. Similarly, you have got 8751, where the program memory is EEPROM programmer, and that EEPROM programmer, this 8751 has an optical port through which this PROM can be erased, and it can be programmed offline with the help of EEPROM programmer. And RAM is also 128 byte. Then you have got 32 IO lines, 1 serial port, 2 timers, and 6 interrupt sources. Then there is an extended version of 8051 which is known as 8052, which provides you 8 kilobytes of program memory, ROM, then 256 bytes of RAM, 32 bytes of 32 IO locations, then 1 serial port. There is 1 additional timer and 2 additional interrupts. So these are the 2 extra. 1 ROM is extra, RAM is extra, 1 timer is extra, and 2 interrupts are extra in case of 8052. So 8051 can be considered as subset of 8052. Then this Atmel 89C51 based on CMOS, where the program memory is flash RAM. So flash RAM is available in 4K size. Others are similar, 1 serial port, and this flash RAM can be programmed through serial port with the help of a program PC. Then your DS 5000, this is also another version of the 8051, where the program memory is NVRAM, non-volatile RAM, which is of 8 kilobytes of size, and you have got same type size of IO ports, serial ports, and the non-volatile RAM can be programmed through a serial port with the help of a program PC. Then of course one-time programmability, one-time programmable program memory is also available. Then Philips has also introduced several 8051 versions where AD converters, DA converters have been included. So this is in nutshell the 8051 family, and you can see what are the varieties available. Apart from this, there is variation in clock frequency. Some are available in NMOS, some are available in CMOS, and so on. So with this we conclude our lecture, today's lecture. We shall discuss the instruction set of 8051 in the next lecture. Thank you.